Welcome back to the Fundamentals of FSP Lab. In this video, we will add the Event Link Controller and Data Transfer Controller modules to automate our ADC and LED so the CPU no longer runs any code in the loop. An ELC is a hardware peripheral in Renesas devices that allows various microcontroller peripherals to trigger each other directly without involving the CPU, acting as a flexible routing matrix for event signals. And the DTC is a peripheral on Renesas microcontrollers that automates the transfer of data between memory and peripherals or between memory locations without using the CPU. To start, open Configuration XML file and go to the GPT timer settings. Enable pin output support. Enable GTIOCA by setting it to true. This activates the timer's output function, letting the GPT directly drive the LED pin without CPU involvement. Change the output pin GTIOC8A to P107, which is connected to LED 3 on the board. You will see a red cross error. That's because P107 is still assigned to GPIO. Go to the Pins tab, find P107 and change its mode to peripheral. This would clear the conflict. Since GPT now controls LED3 directly, we don't need the callback anymore. In the GPT properties, set the callback to null and disable the interrupt. Now go to the ADC module. Change the trigger source to GPT-8 counter overflow. A red error appears. This is because we need the Event Link Controller. So, add a new system stack, Event Link Controller. The ELC allows peripherals to communicate directly. In this case, the GPT overflow will trigger the ADC scan automatically without CPU help. Next, add a transfer stack and select DTC. The data transfer controller moves data between memory and peripherals without using the CPU. In the DTC properties, set transfer mode to repeat, configure one transfer and set the activation source to ADC0 scan end. Click Generate Project Content. Then open Hull Entry C. Add initialization codes for both ELC and DTC using developer's assistance. For the DTC, call RDTC reset to connect the ADC register with G temperature. Finally, in Hull entry, call the ADC scan start once. Previously, we called this inside the timer callback. Now that the callback no longer runs, we must call it here to start the first scan. build a project, and start a debug session. Run the program. Now LED 3 blinks faster. This happens because GPT hardware output is toggling at a 50% duty cycle, so the LED flips every 125 milliseconds instead of 250. Now at the expressions window, you will see that the temperature variable is still updating, but the counter variable no longer increments. This proves the CPU is idle while the peripherals handle everything. To summarize, before implementation of ELC and DTC, the GPT overflow interrupt triggered timer callback function to toggle the LED and start the ADC. The ADC scan-in interrupt triggered the ADC callback function to read the result into the temperature variable. Each interrupt woke the CPU from sleep at the WFI line, so the loop executed and counter incremented. After implementation of ELC and DTC, the GPT overflow event started the ADC automatically through the ELC. The ADC scan end event moved the result into temperature variable automatically through the DTC. And during all this time, the CPU stayed in the wait for interrupt instruction and in sleep mode without waking, so the loop did not run and the counter variable no longer incremented. So this also concludes the fundamentals of FSP Non-TrustZone Lab series. You now know how to create a project, configure modules, use timers, ADC, ELC, and DTC together. So congratulations and thank you for following along.